We did talk a little bit already about the light-dependent reactions in photosynthesis. Gave you the overview. So this should be a little review. Light energy absorbed, converted into chemical energy. Key idea there. Photons of light, so packets of light energy coming in and absorbed by pigments, like chlorophyll, for example. And it's causing a boost in a special pair of electrons in what are called photosystems. So I'm going to see if I can help explain that concept a little bit more in detail through these slides. And as the higher energy electrons move down in energy, they're releasing enough energy transported through an electron transport chain to build up that hydrogen ion gradient on the inside of the thylakoid membrane, the lumen part. So your book talks about light harvesting complexes absorbing light's energy, and I'll explain more with a picture here in just a bit. But they're trying to get that light energy pinpointed into a center area of the photosystem called the reactive area or the reaction area. And it's the special pair of electrons in chlorophyll A molecules within that central reactive area, the photosystem, that is what causes that raised energy level and move and transfer through the electron transport chain. We mentioned cyclic versus non-cyclic, and we're going to emphasize the non-cyclic pathway because it uses both photosystems and talk about it, but then I want to give a brief discussion about why is there the cyclic pathway then for just ATP formation. Okay, so how does energy flow during the light-dependent reactions of photosynthesis? As long as you have light flowing, you have excitable electrons and flowing through electron transport chains. As they do that, there's a buildup of hydrogen ions or hydrogen ion gradient in the lumen of the thylakoid membrane. That would be those green stacks of coins. It would be on the interior of these thylakoid membranes. And that hydrogen ion gradient drives the synthesis of ATP through that special enzyme, ATP synthase. We also end up with NADPH formed, and we'll see that again on the diagram that you've seen. But just to clarify, this diagram is in your book, and it just helps remind you the light-dependent reaction in the non-cyclic pathway. You get ATP, NADPH, and oxygen. The cyclic pathway only forms ATP. This is your book's model of photosystems and light harvesting complexes. All right, so the interior of these photosystems is that special chlorophyll molecule with that electron pair that's ready to be excited, so much so that it can go down the electron transport chains. These other pigments, could be other chlorophyll pigments. These are like pigments that are absorbing light and trying to basically bounce that light in toward the central reactive area. So one way I mentally think about it is it's like the high energy is in the central reactive area, and these pigments out here are almost acting like people on a volleyball team who are bumping it around and trying to set it just to the right spot for that big kill on the volleyball court. And so the special pair of electrons in that reactive area, that's like the one going up for the spike, or you're trying to kill that ball. Whereas these peripheral pigments are trying to direct the light energy in to excite that pair of electrons. This is just another model of the light harvesting complex. So you have these pigments surrounding the photosystem. The photosystem in the center has that reactive area with a special pair of electrons within a chlorophyll inside of there. And these are directing that photon energy to hit that one in the center. This is the cross-section of a thylakoid membrane. So in this particular case, this would be the interior of that thylakoid membrane. This would be the outside of the thylakoid. That's the stroma. And that's out here where Kelvin-Benson cycle would happen in that liquid. This is just another model to try to illustrate the concept of a photosystem in the light harvesting complexes, the pigments that are trying to bounce, almost like a satellite receiver, bouncing that light energy in towards the center, the reactive area. So bouncing it as it comes in and hits these, they're trying to redirect that light energy and focus it into here. Kind of like a satellite dish is trying to bring that signal into that center. So again, photosystem 2, photosystem 1, two different things kind of going on. Photosystem 2 is where water gets split, and the electron from that split water, it gets excited or gets transferred to replace the one that's excited by the light, and that excited energy from that light harvesting complex, that reactive area, gets passed down electron transport chain. In the process of doing that, pumps in hydrogen ions into this interior, into the thylakoid lumen, they call it. Ideally, they would have this green, so you would remember that this is a thylakoid. So water is split, oxygen is released, diffuses out of the cell, and the leftover hydrogens from the water also ending up inside here, pumping more hydrogen ions in here, and so you're building up this concentration gradient that goes out through the special pathway, ATP synthase, a special enzyme that's just designed to build ATP molecules. As hydrogen ions flow out, it causes this buildup of energy that allows ADP to add a phosphate and become ATP. Remember, the ATP is energy needed to drive the Kelvin-Benson cycle. You're also needing NADPH, these electron carriers in the form of hydrogen. So NADP plus added with a hydrogen ion becomes NADPH. All right, so this is the non-cyclic pathway. Electrons excited, get less excited, bring in this hydrogen ion, building up a hydrogen ion gradient, forming ATP. Then the pathway, the linear pathway or the non-cyclic pathway, photosystem 1, used by photosystem 2 as well, excites the electrons and in the process, through an electron transport chain over here, forms NADPH. All right, so you get these excited electrons and they get falling down these electron transport chains. Photosystem 1 can get a replacement of electrons from photosystem 2. However, it was explained to me in a follow-up video that I watched, why does the cyclic pathway happen? And it comes back to, if we go to the Kelvin-Benson cycle, if you look at the ratio or proportion of ATP needed versus NADPH, it needs, I believe, 9 ATP for every 6 NADPHs. But when you're generating the non-cyclic pathway and you're generating these molecules, you're getting a 1-to-1 ratio. What that means is you are going to run out of ATP on the Kelvin-Benson cycle unless you have a way to produce more so that you can have the right proportions of ATP to NADPH. So the cyclic pathway, when this excited electron is raised by the light energy, it can follow this pathway, but it can also fall back and pump in some hydrogen ions that can be used to make ATP and then recharge itself with its own electron. So instead of getting excited and moving this way, it can fall back on itself, pump a little hydrogen ion in for ATP production, and replenish its own electron. Then that same electron can be excited by light, come back down, excited by light, come back down. Every time it comes back down this direction, it makes hydrogen ions pump in for ATP production. So in that way, with the cyclic pathway, you can boost your ATP amounts to get the proportion you need for Kelvin-Benson cycle. So photosystem 1 can be used one of two ways. The non-cyclic, where it's getting its electrons replaced from the photosystem 2 pathway, or it can cycle back on itself and replace its own electrons. So it can do both. Makes it versatile. All right, moving on. Non-cyclic pathway then uses both photosystems, 2 first, then 1. You need water because in photosystem 2, water gets split, a process called photolysis, and oxygen is released. The electrons from the center, the reactive area of the photosystem, fall along electron transport chains, losing their energy. As they do, they pump in hydrogen ions for ATP production, because that's what that hydrogen ion gradient allows for, is the production of ATP. And they call that electron transfer phosphorylation. All right, the cyclic pathway. When NADPH accumulates in the stroma and the proportions are not quite right at the Kelvin-Benson cycle, we might need to access some more ATP, and that's when the cyclic pathway takes over. And so, as I just tried to explain, it can take those excited electrons, instead of going along the non-cyclic pathway, it feeds back on itself. In doing so, those excited electrons give off hydrogen ion, or pump in hydrogen ions and generate ATP. So no oxygen is produced from the cyclic pathway because water is not being split here. So, and then we got to the light independent reaction today and went through that together. So here ends our accessory notes screencast to add a little more detail to adjust the slides along.